Okay, so hi, and thank you for coming to our talk. We're two persons showing this talk, so we'll present quickly ourselves. I'm Manu. I work for Criteo. I'm the leader of the DevTools team there, which means that we're responsible for making the best, creating the best possible development environment for all other developers there. We are something like 200 developers.
And that's okay. I'm Adrian Perreau, and I was... it's actually Adrian Perreau, so it depends on your language of choice. I was a program manager at the same team with Manu, helping these tools be put in place. Now I work at Agilar, so we help other companies do things like that and be more agile.
So today we'll be talking about scaling, and scaling for a software company can mean different things. Usually we think about scaling as scaling the number of requests per second that our servers can handle.
Sorry. Ooh. Sorry.
So usually we think about scaling as the number of requests per second that our servers can handle and the amounts of data that we can store and process. So in that regard, Criteo has scaled quite a lot. We are currently dealing with a Hadoop cluster that stores more than 38 petabytes of data. That's a lot of data. We serve more than 1 billion. It's actually a lot more now than 1 billion.
This is the Spanish billion. It's like 1 million millions, right? It's not the 1,000 millions.
So 1 billion ad impressions per day, and we have a lot of servers. However, this is not the kind of scaling that we are going to talk about today. There's another kind of scaling that we had challenges with, and it's scaling the number of developers in the team, scaling how many features they can develop and release and deploy during a certain given time. And this is something totally different that we're going to talk about. So if you work on a pet project, an open source pet project, for example, where you're alone and you're just developing this tiny thing on your own, you know that the setup that you require to make it easy to change things is actually minimal. Even if you say you go in holidays for 2 weeks and you come back, your setup is still there, your PC is still there, your code is still compiling, you can still change a few lines, push it to GitHub, and then release a new version with that new feature. If you work on a team, like on a five-ish people team, you probably need something more, like you need more of a setup to make sure that it's possible to interact together and to change the code together. Maybe you need like a nightly build or something. You need something that I don't know what precisely, but you need something that will run your unit test or something that makes sure that when you are committing code, you're not breaking the others' code, and when the others are committing code, they're not breaking your new features and stuff like this. And our argument here is that this complexity, like how hard it is to change code, grows more than linearly with the number of developers when you're adding developers to the team. I don't want to, so the curve here is quadratic. I don't want to argue whether it's quadratic or not, but it is definitely more than linear. And an easy explanation for this is that when you add a new engineer in a team, is going to work on a new module. And this new module is not going to be something that's independent of all the rest. It's going to be probably even like tightly coupled with all the rest. And in these interdependencies lie complexity. The sum of the complexity of all of your different modules taken separately is smaller than the complexity of your product because of all of these interdependencies. And this means that you need to be super careful about something. You need to be really careful about like the way you set up your development environment, because otherwise you're going to end up like this. And if the curve looks like this, it means that at one point you're going to be adding more developers and they are not going to add value. They're just like going to make it more complicated for everybody else to release code. So we'll tell you a story today. We'll tell you the story about Criteo. We'll tell you how it was way before when we started feeling these problems. Then we'll tell you how we tried to fix it, and failed. And then we'll tell you how we tried to fix it again, and we think we've succeeded so far.
So, once upon a time, right? We start stories like this. Once upon a time, we had a single C# repository. And this C# repository ruled everything. All the code was in there. All the millions of lines of code were there. There was C#, there was ASP also, but mainly .NET stuff, right? And when you tried to build this thing on your machine, it was taking 90 minutes. And this is only build, this is compile on your machine. And we had pretty powerful machines because we're a high-tech company and they were putting money into these machines, and it was still taking 90 minutes. So what happens when you're doing some code change in your repository and your feedback loop for knowing whether it compiled or not is 90 minutes? You either go for lunch, or you look into this build script that you have, which is pretty complex because it's 90 minutes worth of build script, and you say, okay, this is not impacted, so I'm just going to comment it out. And I'm going to just build the stuff that I think is impacted. Of course, when you join the company, this is not easy to do because you have no idea which of the 7 million lines of code that we have actually is impacted by your changes. So you have to have one of the senior guys in the team come and help you tailor your build script so that you can compile in like 5 minutes, 10 minutes.
Plus it looks like it's really simple here, but it's not a real life example.
This is not the real life. Right? And then if you are an engineer that cares about quality and stuff, then you go and you look for your Jenkins. And it's hard to find. I mean, they weren't publicizing Jenkins. Jenkins was actually hidden under someone's desk. And you came in and it's like, oh, so where's our continuous integration build? It's like, oh, somebody has Jenkins over there. So you could go and add a job on it because it was basically some developer that was maintaining it. But most people that didn't know about this or didn't care about this were not putting their stuff into this Jenkins machine. So it wasn't really continuous integration. Jenkins was hiding. And then once you modified this change, you wanted to check whether it was doing what you expected. But actually running this application was very, very hard. So it really meant that you had to set up a bunch of things on your machine to get it to actually run with all the dependencies in place. And this, again, was a very hard job, which only some of the senior engineers knew how to do. So they were the ones that were ending up testing the stuff on their machines before they were deemed good. And there was this culture of testing is cheating. We're all so smart that if you have to write a test to check that the thing does what you think it does, it means you're stupid. That was the culture at the company at the beginning. So how did the process work before we tried fixing it? So there were a bunch of developers, and they all worked on their separate branches, and once they thought they were done, they would send merge requests to the central repository. And then there was one guy that would try to merge everything, and there were conflicts. So he would run around the department trying to figure out what the conflict was and trying to fix it. If he managed to do that, great. If he didn't manage to do that, he would have to kill some branch that was doing the problems and try to merge the other ones. And once he managed, he would pass to the next step, which is try to build it. So actually run the build script with all the merges, etc., and see if that worked. Same process, again, for deploy. He would grab that, put it in a production machine without traffic, and try to execute it and see if that worked. And if that worked, he would send an email to all the guys that had sent the merge request, say, can you please test that it still works now that we've integrated a bunch of code? So they would go, they would verify that their features were working on this machine, and if they said, yes, it all works, they would put some traffic in. We had some traffic serving banners. It's just one machine out of 4,000, so if it breaks, it's not a big problem. And if it did work, okay, roll out to the rest of the data center, roll out to the rest of the data centers all over the world. And this process, when we were 20 engineers, it was taking 3 days. So 3 days in a weekly cycle, that's okay, that's doable. Then we grew to 50 engineers. This did not even take a year. We were doubling in size every year. So after a year, it was taking 4 days to do this because there were more branches, so it was harder to pick out the ones that weren't working. When we grew, oops, now you know what happens.
You saw the train wreck.
Okay, so after 140 engineers, it actually became 5 days that it was taking for this to happen, and then one day, one day there was a train wreck, meaning that we hadn't been able to do the whole process for the set of merge requests for 1 week, and the next week merge requests came in, which of course we were building on the previous merge requests. Because people were not like, okay, we send you the merge request, we stop programming, and when you tell us it works, we continue to program again. No, they're continuing to program on top of that, and then they sent another merge request the next week. Didn't work, we had to think of something else. So which one was our first attempt at fixing this? So we brought in the architects. We hired a senior architect, which looked at the code for a long time and decided, with some of the senior engineers in the company, that we should look at an open source model and have an internal open source model in the company, meaning that we would split this repository in order to have separate repositories where each team was touching a subset of all the repositories. Therefore, there would be less branches to merge into the repositories, and it would be easier. And of course, we had to split the repository into repositories. And it worked. I mean, there were less branches being merged into each repository, so it was easy, and we had to add nuggets. How many of you know nuggets, C# world? So nuggets is the de facto standard for packet management in C#. It's basically the Maven of the C# world. Okay? And basically what happens here is, let's see, oh yes. You have repo A that uses code in repo B. So what you do is you change something here, you build it into a nugget, and that nugget gets published into a nugget server with a version number. You do the same thing for repo B, and this is published independently, so everybody could now change code, compile it, publish some nugget, perfect. And this guy, he was safe because he could decide at this level what version of nugget B he was using. So even though we were deferring integration, it was awesome because we didn't have to worry about crashing because of somebody changing something somewhere else in the system. But this has problems. By 2012, when we did the first split, there were 33 repositories. So what happened? They split the repositories along the lines that the architecture wasn't great, so they said, okay, we're going to split it here, and because of the pain of moving through repositories, an architecture will emerge. So what ended up happening is, actually, since there was so much pain, what people were doing is, I'm going to create more repositories to fix the problem where you have one repository using code in 2 repositories, and then you create a third one so that you don't have to depend on all of that. So in 1 year, we went from 33 to 160 plus repositories. And this was not manageable. By this time, we had basically 1 repository per person. This does not mean that I have my repository and you have yours. It means that I'm touching 5, you're touching 5, and it was just a big mess. And we had spaghetti and nuggets. It's a new dish, French cuisine. This is part of the dependency graph that we picked from the actual code. There were a bunch of nuggets. The lines are dependencies. This is just a small part of the graph. It goes probably like from way over there to over there, and it's 26 levels deep. And of course, a lot of these repositories were not being owned because nobody wanted to take care of them. So when you had found a bug somewhere in one of the repositories, it was a pain in the ass to get someone to fix it. So we said, hey, you guys, you all need to own, as a team, all repositories need to be owned by some of the teams, which basically means now I can blame people for not having the repository correctly, and it also means we have component teams, which was the best we could do at the time, and we still have a bunch of them, But it also means that things are slow because if you have a feature that impacts many repositories, there's many teams involved, and even though you can do merge requests to other repositories that you don't own, you still have to wait for them to approve them. So it's a lot of overhead. And for those of you that don't know Conway's law, it basically states that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. In our case, the team boundaries weren't clear and the interfaces between these teams weren't clear, so we had the same problem in our code, and this actually made more conflict appear because they were fighting over, no, this is your repository, no, this is my repository, no, your repository sucks, blah, blah, blah. And there was a big problem with propagating changes. So let's say you have one repository and you change it, it's fine, you publish it, you're done, but this doesn't go in production until somebody from a top-level repository uses the latest version of your code, right? And you had to convince that person to do that, and he was afraid of doing it because he was afraid that your code might not work, and he was happy with using an old version. In one case, actually, we were going to go public as a company, so we had to do Sarbanes-Oxley. And in order to do that, we had to do a bunch of technical things. And one of them was touching the SDK. The SDK was the lowest level of this 26 layers of hierarchy. And of course, all the guys in the top level application were saying, oh no, please don't change the SDK because we're going to change everything. And it took a program manager and a bunch of senior engineers more than a month to make all the top level applications use the latest version of the SDK. Some of these top level applications were 5 major versions behind, so they were months behind because they weren't being forced to update to later versions, so they weren't doing it. It was a risk.
And also note that this change he's talking about is like a 100-line change in in a few files. So it should not have been that tough of a problem.
And then we had the release problem. Right now, I guess there's also a code freeze going on because it's the Christmas period, and this is an advertising company. So
it's shorter now, I think.
It's shorter now, it's good. Yeah. But back then, it was a month. So they said, okay, for a month, it wasn't really a code freeze, it was a release freeze. You do not put anything new in production because if something fails now, we're going to lose a shitload of money, right? So just leave it as it is. And we promise from the business side that we won't ask for anything new. But this was not true. We all know that when they promise that, they don't really mean it. So developers were continuing to develop for a whole month, so they had this huge things to put into production once the release was, the freeze was over. And when the freeze was over, all these changes took, over 1 month of code to integrate, and in some cases it took 5 months to be able to release some of these applications again. And we continued to grow. So this wasn't scaling. The team had almost doubled. If we did this again next year, it might take us 10 months to release. And if it took 12 months to release, we would come into the next cycle. And this is similar to what was going on week per week, but at a year per year interval. And we might just crash the company. Oh, no, this is your side now.
So Adrian has explained all of the different steps that led us to this failure. I'd like to take a step back and try to explain what I think were the 2 big mistakes in this. I think that the first big mistake was to let this poor guy with the glasses there, the owner of an application in production, integrate the change of all of these developers. So we had like 100 developers. What they were doing all day was writing new code and checking it in the Nugget server and stuff. And then there was this one single guy whose job was taking the new versions of the Nuggets and integrating them. And if it worked, pushing them in production. If it didn't work, go back to the developers and tell them that it doesn't work and stuff. And obviously it doesn't scale, right? Because there is one here and there's a multitude here. So I think this is the first big mistake. The second big mistake, I think, is that we allowed late integration of changes. So we allowed developers to develop something and to think that it's finished. They were pushing it on the Nugget server and they were like, yeah, I released my version 3.0 and they think it's finished, but it's not finished because it's not used in production yet. It's not used by anybody yet. Maybe they have, even if they have unit tests and everything, they think that it works, but their contract with the application was not clear, and it's like actually not working. And they'll know only in 2 weeks when the application integrates their new version of their nuggets. So I think these are the two big mistakes that we made. At that point, in the company, we really were aware of these problems. We really felt them. So a group of us joined forces, got together in a room and wrote this big document that states exactly all of the problems that we were having and that proposed a plan to fix it. Note that in this group was a senior vice president of engineering, so we had the right level of executive support to do this, because otherwise it would probably have been impossible. It was all themed as a metrics saga, because taking the red pill means like seeing reality as it really is. And so what we pushed for is simple. We pushed for early integration instead of late integration, and we pushed for automating the dependency, the flow of commits to top-level application without having versions in between. So what we said is we are not going to allow code in applications to depend on old versions of the code in the components. We will force all applications to depend on the latest version of the code that has been checked in. So this is exactly what we did, and this in the literature is what is called trunk-based development. Trunk-based development is not something that we invented. It's something that's used in other big companies, like Facebook is doing this, and they have quite a few more engineers than we do. And Google is doing this as well, and they have quite a few more engineers than Facebook has. So we knew that it was possible to make this scale. However, we also knew that there were very big problems with trunk-based development. Namely that I think that two things are really hard. Like it's a real pain to work with this. And the first thing that makes it painful is what I call the football in principle. And it states that whenever somebody in your company checks in a commit that is broken, you're actually, until he fixes it, you're actually paying your developers to play football in instead of writing code. And it's a very big difference from the other model, right? Because in the other model, you were checking in code that was broken, but nobody was depending on it yet. They were depending on an old version of your code. And obviously, you would wait a bit and then release when it's stable, and then people would depend on that version that was not broken. But now, when you're pushing a commit, then all of your dependency, all of the people who depend on you, they immediately pull this commit within their application, and if it's broken, then it's broken. It might not even compile. Before working for Cupcic, I worked for Google, where you on your profile page at Google, you have badges that you earn when you do like cool things. Like you earn like cool badges because you've done cool things. And one of these badges is when you break Gmail once, you get one of these badges because you've like bothered like I don't know like 600 engineers for like an hour or something.
Did you break that one?
No, I didn't break this one. I had other badges, right? And then you can really feel the pressure of everybody like coming to your desk and trying to tell you to revert this commit at once because they're impacted by it. The second thing that is tough when you're working with trunk-based development is that in the old model, it's very easy to change like a big interface in your component. You can say, okay, I'm going to change everything. This method is not going to be called like this anymore. This class is going to disappear and going to be is going to be replaced by this other class and stuff. And then you release a new version of the component and you say, well, guys, you're using it. Please update all of this. You have a changelog that says you should change it like this and stuff. And this is impossible, obviously, with trunk-based development, because at the instance when you do this, even if you put the changelog somewhere, well, you're breaking everything. So everybody's like no, you cannot do this. So you need to develop techniques like branch by abstraction to do this, which is basically creating these branches inside your code rather than inside your SCM system. So it's a real pain to work with trunk-based development. However, we love it. And the single one reason why we love it is that there is not ever going to be someone who comes back to your desk after 2 weeks and says, do you remember the feature that you coded like a while back, like 2 weeks ago? Well, it's not working in my case. This never happens because at the exact instant where you check in the code, it's used by everybody else. And since it's used by everybody else, they can know immediately whether it's broken for them or not. And if it's broken for them, then they will come back to you, but they will come back to you in, say, 10 minutes or maybe an hour, but not 2 weeks. And this is a major difference. And I think that I think that this is like more agile, right? Because when you've finished a task, then it's finished. Nobody is going to come back to you in 2 weeks to tell you you thought it was finished, but it's not. So what did it take to do this? We had this group of people. We formed a team from some of the people that were in this group and some other ones. And we had a team of about like 9 people, which was a quite big team compared to the size of the R&D at the time. And with this team, we've done 3 things. The first thing that we've done is we've built the infrastructure that can do this. So we've built, it's not trivial for C#. It's probably easier if you're working in other languages, but for C# it's not trivial. We've built the infrastructure, which means that we've built tools that check out multiple Git repositories and build everything concurrently. We've created Jenkins servers with many slaves, like we have like something like 40 Jenkins slaves to build all of this. And we've spent quite a bit of time to build something that makes sense and that's like powerful, because if it's not powerful, then people won't be using it. Then we had this big project to be able to come back to building from the latest source code in all repositories. And that was not trivial, right? You had applications that were depending on nuggets at this version, and these nuggets were depending on lower nuggets at other versions, and so on, 26 layers deep. So what we did is we told everybody, listen carefully and be careful, because on this exact date, I think it was December 2nd, 2013, something like this, on this exact date, we are going to be reverting all of the commits of all of your components that are not in prod somewhere. So this sentence scared the hell out of them, and they were very careful to put in production everything they could before that date. And
we actually put them all into a space like this one and pressed the script to do the revert in front of everyone so they saw it happen.
Yeah, this is true. I forgot this, but this is true. So, and at that point, we reverted all of the commits that didn't make it to prod somewhere, and we started building the thing from the latest source code everywhere. At the beginning, we were something like at 50%. That means that 50% of the project from the bottom up were building, but not all of the other ones, because they were depending on things that were not there yet or not there anymore. And we displayed the percentage of the build that we were achieving currently everywhere, and we kind of gamified it. We tried to push everybody to fix all the compilation problem until we managed to get to 100%. We actually got to 100% faster than we thought. I think we had a week to do it, and we did it in 4 days, which is good. And then the plan was to, once this is working, to try to deploy the application in pre-production, and then put some traffic on it, see if the graphs fall down or not. If they don't, then it's a good thing. So this occupied only a few engineers per team, not everyone. All of the other ones, the only thing they were allowed to do during that time was writing tests. We didn't code any feature for a whole month. The only thing we did is get this build back to green and write more than unit. It was not only unit tests, it was unit and integration and end-to-end tests. So now that I've explained everything that we've done to make this happen, I'm going to give you a bit more detail into exactly what is our technical setup. So we use Git at Perreau. We have, as Adrian said, we have more than 100 Git repositories, and we use Gerrit for code reviews. So every code that is changed goes through Gerrit. So basically, what engineers do is they change the code, they send they do a Git commit, they send it to Gerrit for review. What this does is this sends an email to humans to actually have a look at the code, tell us if the variables have the right name and if the design is okay. And it also sends an email to Jenkins, which will choose a slave, check out the latest code, patch your review on top of it, runs all the relevant tests, and tell you if the relevant tests still pass or not. If all of this is good, the humans are okay, and Jenkins is okay, then the code is checked in. And then starts our big Perreau continuous integration pipeline, which we call the MOAB. MOAB stands for Mother of All Builds. What the MOAB is basically this big Jenkins job that runs continuously. It takes something like 9 minutes, and it runs continuously, meaning each time it finishes, it starts again from if there are new commits, it starts again. And what this job does is very simple. It clones all of the Git repositories. It fetches the latest source code on it. It resets hard the current pointer on all of the repositories, and then it tries to build them. And we have this tool that builds all of the thing in parallel, so it's fast. And once everything is built, or it's not building, and then we send emails to people to fix it in the very urgent manner that I described before, or it's green, and then what we do is we zip all of the DLLs that we've created together, we store them on a filer, and we write down all of the shell ones that created these DLL, and we store them alongside. So these are excerpts from the actual script. I just changed the number of projects so that you don't know how many we have. And then at the end of this starts our continuous integration pipeline, where first we run all of the unit and integration tests, and then we run all of the end-to-end tests. So the end-to-end test is basically we take applications, we deploy them on test machines, and then we run traffic against it. We run queries against them, and see what the results are to make sure that they're responding okay. There is this concept of claiming the build, which means that when one tile in this setup is red, then it's very urgent for us to fix it. And in order to communicate about this with the rest of the team, one individual can claim the build. It means put this picture. It's very simple to put your picture up there. And that means, okay, everyone, I know what the problem is. I'm working on fixing it. It's going to be, this is my most important task. It's going to be fixed very soon. So we have this, and sometimes people claim several parts of it. And what we try to have is mostly green and no red, or only orange tiles. Orange tiles means claim.
There are screens with this all over the building.
Yeah, people talk about this. It's something that is quite important in R&D. Oops, this is the same thing again. Okay. Just a side note about end-to-end tests. End-to-end tests, we do not run them on actual data center. We made a data center very small to be able to put it on one Linux VM and one Windows VM. And this is what we call the sandboxes, and this is where we deploy applications to run the end-to-end test. Another thing that is interesting is how we deploy things in the actual data center. What we do is basically we SCP the binaries on one machine, and then we use BitTorrent to copy this onto all of the different machines. At the end of the pipeline, after all of these end-to-end tests have run, we take the application, we deploy it on an actual real production server, and we put 1 hour of traffic on it. If we lose all money on this 1 hour of traffic, it's not that bad. It's only one machine. It's okay. And at the end of this hour, we monitor the graphs. So we monitor all kind of graphs on this machine, and we automatically make sure that they look the same as the other production machine during that time. So we have algorithms that check the graph, and that make sure that these graphs look the same as the other ones. If they don't, then we raise an alert. If they do, then probably everything is okay. And this is how the graphs look. On the left, you have one graph that doesn't work. You see that the blue curve is really it's really too far up compared to the gray curves, and on the right you can see that it's okay. So these are the kind of things that we do to be able to automatically know whether it's a release looks okay or not. Because if we didn't do this, we would have like thousands and thousands and thousands of graphs to have a look at all the time.
We actually had some guys at the beginning look at the graphs by hand in order to give input so that the algorithm that would check automatically knew what to do later on. And this was a very painful job. Yeah. So as conclusion, basically, is that we managed to change the graph, right? So the point here is that before we had a quadratic between number of devs and cost of change, and we've actually made it go down. So now we're getting lower cost of change for each dev we add for the department, because basically we have a percentage of these developers which are fully dedicated to this build system. So this build system is every time going faster and faster, and we're managing to make the time of feedback be lower and lower, and we're able to go faster in adding new features. Oops. And we're not the only ones that went through something like this. LinkedIn, which you all probably know, had to go through this at one point. They weren't able to scale, so they decided to stop the development pipeline and go through the re-engineering. They actually stopped everything. We only stopped for a month. I think they stopped for longer, so we're better. And Etsy also went through something like that. And so it's something that looks risky, but sometimes you need to do it in order to continue to scale if that's what you want to do. And that's what Criteo wants to do, right?
Yeah. So yes, thanks to this, we are able to grow again, and I'd just like to say that we are hiring all across the board. We're hiring engineers, but we're also hiring people to make sure that the engineers can work on new features and stuff to facilitate the way teams work together. All of this, so currently we're like something like 200 developers, and we are hiring 130. So today in R&D we're something like 200, and we're hiring 130 this year. So it's going to be a real hiring challenge. So if you're interested, come at the end of the presentation. You can come talk to me, and I'll tell you more about it.
And if you do this in your company, you can hire us.
So this was it. If you have questions, then feel free. I don't know if there's a mic for you, but maybe there's.
Yeah, that's the mic that I want to use these.
I have a question. I've seen this among many different companies. So my question is, why do people execute the test after the commit, but not before? So if you do execute them before not the commit, sorry, the push, before the push on a Jenkins machine, you are always sure that your code compiles and is green.
So what you're saying is, I showed the, sorry. So what you're saying is that I showed the picture where we run, before the commit we already run the test. So you'd like to know whether it's worth it to run them again afterwards. So I have two answers to give. The first one is that we do not run all the tests before. We want this feedback loop to be as fast as possible, because the guy can change like little things in his code. Basically, it's a code review. So people will tell the author, please change this variable name. So we don't want the guy to have to wait for an hour until he can submit it. So we run all the tests we can that last less than, say, 3 minutes. So we do not run all the tests. That's the first reason. And then second, you can have problems where there are two commits that are incompatible. They're tested independently each, and they each work independently. But when you merge them at the same time, then they don't work together. So you still need to rerun the test afterwards, even if otherwise you would need to run the test all the time and to fix all of these conflicts at integration time, which is tougher. So we also run them all after. But basically, the main answer is we run 3 minutes worth of tests, and then afterwards the pipeline is much longer. It takes like something like today, it takes something like, it's less than an hour, but it's 40 minutes long. So it's not acceptable to have it at review time.
Hey, you mentioned that you have like a sandbox environment that you use before deploying to production. My question is, when a developer is developing on its own machine, and imagine that it's working on the product A that uses 3 different APIs, whatever, those APIs, they use the sandbox environment or they use the production environment for those APIs? You know what I mean?
So I'll try to rephrase your question. I think that your question is, what do the developers do? Do they have access to the sandbox environment, or did they code against some other environment?
Yeah, while they are developing, they use the sandbox environment for
okay. So our plan is that in order to develop, they should use the sandbox environment. However, it's actually tough to deliver VMs on demand per developer, so we didn't have time to do this yet. It's in our objectives for next year. Currently, they do not use a sandbox, and it's a shame. Currently, most developers, they use only their unit and integration tests to test the stuff, and some of them need to have a proper working environment, and then they come to us and we lend them a sandbox. But we don't have like an on-demand system for sandboxes, which is a real shame. But we couldn't do everything.
Thank you.
You can ask in Spanish too. I understand Spanish.
Okay, well, if you don't have more questions, then I guess this is it. Okay, so hi, and thank you for coming to our talk. We are 2 persons showing this talk, so we'll present quickly ourselves. I'm Manu. I work for Perreau. I'm the leader of the DevTools team there, which means that we're responsible for making the best, creating the best possible development environment for all other developers there. We are something like 200 developers.
And that's okay. I'm Adrian Perreau, and I was... Yeah. It's actually Adrian Perreau, so it depends on your language of choice. I was a program manager at the same team with Manu, helping these tools be put in place. Now I work at Agilar, so we help other companies do things like that and be more agile.
So today we'll be talking about scaling, and scaling for a software company can mean different things. Usually we think about scaling as scaling the number of requests per second that our servers can handle.
Ooh, sorry.
So usually we think about scaling as the number of requests per second that our servers can handle and the amount of data that we can store and process. So in that regard, Criteo has scaled quite a lot. We are currently dealing with a Hadoop cluster that stores more than 38 petabytes of data. You are committing code, you're not breaking the others' code, and when the others are committing code, they're not breaking your new features and stuff like this. And our argument here is that this complexity, like how hard it is to change code, grows more than linearly with the number of developers when you're adding developers to the team. I don't want to, so the curve here is quadratic. I don't want to argue whether it's quadratic or not, but it is definitely more than linear. And an easy explanation for this is that when you add a new engineer in a team, is going to work on a new module. And this new module is not going to be something that's independent of all the rest. It's going to be probably even like tightly coupled with all the rest. And in these interdependencies lie complexity. The sum of an open source pet project, for example, where you're alone and you're just developing this tiny thing on your own, you know that the setup that you require to make it easy to change things is actually minimal. Even if you say you go in holidays for 2 weeks and you come back, your setup is still there, your PC is still there, your code is still compiling, you can still change a few lines, push it to GitHub, and then release a new version with that new feature. If you work on a team, like on a, say, a five-ish people team, you probably need something more, like you need more of a setup to make sure that it's possible to interact together and to change the code together. Maybe you need like a nightly build or something. You need something that I don't know what precisely, but you need something that will run your unit test or something that makes sure that when there's a lot of data. We serve more than 1 billion. It's actually a lot more now than 1 billion.
This is the Spanish billion. It's like 1 million millions, right? It's not the 1,000 millions.
So 1 billion ad impressions per day, and we have a lot of servers. However, this is not the kind of scaling that we are going to talk about today. There is another kind of scaling that we had challenges with, and it's scaling the number of developers in the team, scaling how many features they can develop and like release and deploy during a certain given time. And this is something totally different that we're going to talk about. So if you work on a pet project